Are there any questions over the homework? Any questions over the homework before we get started today? Okay. No cheat from yesterday. No cheat from yesterday. Yes. Now, when writing transformation of a quadratic, the lowest point of a parabola that opens up, or the highest point on a parabola when it opens down, is the vertex. So what they're talking about here is if we graph, you don't have to draw this here, a parabola that opens up, the lowest point here is called the vertex. If it opens down, the highest point is the vertex. And that's actually the minimum or maximum value. And it's called the extrema, the maximum, so it'd be the extrema for maximum or minimum, because it is the lowest point or highest point that we can have, depending on how it opens. Is this point here, because it can't get any bigger than this one here, or any lower than this. But on parabolas that open up, we won't actually have a maximum value. Because no matter where I pick a point going up, there's always going to be one that is bigger than it. But we have this here. This is vertex form. And the reason we call it vertex form is, well, the h comma k, hk values give us the vertex. So it's called vertex form. Now, there are three main parts, and we've had these before. The a value indicates a reflection in the x-axis if it's negative, and or a vertical stretch or shrink. The h value indicates a horizontal translation, and k indicates a vertical translation. And we've talked about these before with this a, h, and k, and how we apply these transformations. Because we talked about our horizontal transformation left to right is our f of x minus h. Our vertical translations is our f of x plus k. Our vertical stretch, and I'm not doing these in any particular order, shrink is our a of f of x. Our horizontal stretch slash shrink is our f of ax, and we do have to flip a. Whatever the value of horizontal stretch or shrink is, we have to flip it to get the correct value that we plug in. Our reflections across the x-axis is negative f of x, and across the y-axis is f of negative x. And we had these 6 here for applying transformations, and really that's what we're going to be looking at today, is applying these transformations here to our functions. Okay. So if we look at this first one here, let the graph of G be a vertical stretch of by a factor of 2, reflection in the x-axis, followed by translation 3 units down of the graph f of x equals x squared. Write a rule for this here. So we have 3 different transformations. We've got vertical stretch of 2, reflection in the x-axis, 3 units down. And we're going to do these in order. So the first one, I'm just going to call it h of x. Vertical stretch by a factor of 2. Our vertical stretch is our a times f of x. Now our value of a in this case is 2. Because it's not a horizontal stretch or shrink, so we don't have to do anything to the 2. It's just 2, because vertical would just be 2. And we fill in the information. Now we need to replace f of x with its function. And f of x function is just x squared, because it told us the graph of f of x equals x squared. So it's just x squared. Is going to be next, yes. The last thing for h of x is we multiply this here, giving us 2x squared. Questions on our vertical stretch of 2? And yes, our next one would be reflection in the x-axis. So we'll call it, say, m of x. So to do a reflection in the x-axis, we take negative and apply it to the front. It'd be negative f of x normally, but we're not applying it to f of x. We're applying it to h of x. So it's just negative h of x. Our second step is to apply that to it. So it's negative h of x. We still have the negative, but we're going to replace h of x with what it equals. And h of x functions was 2x squared. So we have negative parentheses. So it'd give us negative 2x squared. Questions on how we did the vertical stretch of 2 or reflection in the x-axis? Followed by translation of 3 units down. So our 3 units down would normally be f of x plus k. But instead of applying it to f of x, we're now applying it to m of x. So just m of x plus k. And k is the amount that we move the function up or down. Here we're moving it down 3, so k is 3, but it wouldn't be positive, it would be negative because we're moving it down. And what's m of x? Negative 2x squared. Our function is negative 2x squared minus 3. Questions on this here? Okay. We ready for the next one? Let the graph G be a vertical shrink by a factor of 1/2, followed by translation 2 units up of the graph f of x equals x squared. Identify, write a rule for G and identify the vertex. So this time we have now the first one's a vertical shrink. Well, the form for our vertical stretch or shrink is our a f of x, where a is the amount that we're stretching or shrinking the function by. Well, our a value in this case is 1/2. What's our f of x? Same thing as was last time, x squared. So we multiply this, it would give us 1/2 x squared. Questions on this here? Done. Now the only other transformation we have for this one here is a translation 2 units up. So this would normally be f of x plus k. But since we're not applying it to f of x, we're applying it to h of x. We would say that g of x equals h of x is our 1/2 x squared plus 2. We do plus 2 because it's moving up 2. Minus that g of x is equal to 1/2 x squared plus 2. That's it. Questions on this here? I believe this is the last one we have, yes? Let the graph of g be a horizontal shrink by a factor of 1/3 and a reflection of the y-axis followed by a translation 2 units up of the graph of x squared. Now, the way they've listed these out up to this point so far, they've done this in a particular order for a particular reason. Because here they said a parentheses x minus h close parentheses squared plus k. That's what they gave us. Now, here, and the way they did this, I'll show you this here. Now, this works if they put in this particular order in this way in this setup. Here, vertical stretch of 2, so A is 2, yes? Reflection in the x-axis, that's also A. So A is technically, we'll have the negative and the 2, yes? So that means I can come here and replace this A with negative 2. It didn't move it left or right, so the value of H is 0. 3 units down, so K would be negative 3. We apply it here. We would still have the negative. What's x minus 0? Just x, yes? And it would still be squared, so we have x squared plus negative 3, or we could just say minus 3, yes? And that's what we got. That's kind of nice, a little bit easier, yes? But that's only if they list the stretch or shrink first, the reflection second, and then the translations last. If they do stretch and shrink, reflections, then translations, it works like that very nicely. If they do the translations or in any different order, we can't just do this. Does that make sense? So it's not that I don't want to show you this because it's too easy, it works. This works in this one way, in this one order. Does that make sense? I would rather show you the way, because the way we do it works in any order that we list the transformations. Doesn't matter, it always works. This works in this only if it's set up this way. You all see the difference? I would rather give you a way that works every time, not one that works if it's set up this way. Because if we switched any of these and put the translation 3 units down first, we have to apply that factor of 2, that vertical stretch, to the negative 3, which would change it to 2x squared minus 6. So, there are some ways that work nicer, but this here only works in this way. This one here, let the graph G be a horizontal shrink by a factor of 1/3. So the first thing we want to do is apply this horizontal shrink by a factor of 1/3. I'm going to call it m of x is equal to f of a times x. Because our f of a times x is our horizontal stretch or shrink. Now the value they gave us for the stretch or shrink was 1/3. We're not going to plug in the 1/3. We have to flip it. So it's going to go from 1/3 to 3/1, which is just 3. So we're going to plug in 3x, not 1/3 x, because it's horizontal. Now our normal function was that f of x equals x squared. So instead of having x squared, we have parentheses 3x, close parentheses, squared. We replaced every x in f of x with 3x. That just becomes this here. Now at this point here, we can leave it as parentheses 3x squared. We can leave it in that form. We don't have to simplify. So that takes care of the first transformation. Now we have a reflection in the y-axis, called h of x. So a reflection in the y-axis is normally f of negative x. But we're not applying it to f of x, we're applying it to m of x. So a reflection in the y-axis would be m of negative x, which means we're going to replace every x in m of x with negative x. Yes? So let's see how that looks. H of x equals. Well, m of x, we have the parentheses. We still have the 3. But instead of x, we have negative x. We replace the x with negative x. What's 3 times negative x? Negative 3x. Reflection of the y-axis is done. And the last is our translation up or down, which is our addition of k. So here would be h of x plus k. And exactly, since we're moving it up 2, we're going to add 2. And our h of x is our parentheses negative 3x squared. Questions on this here? Now, especially back in chapter 1, there was one of the problems that had a reflection in the y-axis. And some of y'all did put, because it ended up being negative 6x plus, I think, 2. Interestingly enough, this here is also the same answer. For this one here, g of x equals parentheses negative 3x squared plus 2. This is actually the same answer. And there's a reason for it. It is dealing mainly with our properties of x squared. Because when we square something, we're saying that we're multiplying it by itself, yes? So the 3x squared, and we'll put this here, 3x squared, so we're saying negative 3x times negative 3x, yes? So what is negative 3 times negative 3? Positive 9, yes? X times x would be so we get this here. So really, our parentheses negative 3x close parentheses squared is the same as 9x squared. Now, if we had a horizontal translation left or right, we would have left it, because there's no reason to do that. It makes it harder. Here, since it's a single term, we can say this here. Now there's a question, why did we change this? Well, okay. My marker back. Properties of absolute value. We'll not worry about the 2, because this mainly this part here. I can say it's negative 1 times 6x, yes? I mean, it doesn't make a whole lot of difference, but we can say that those two are the same, yes? One of the properties of absolute values is that the absolute value of m times n is equal to the absolute value of m times the absolute value of n. We can split it. So here, I can say it's the absolute value of negative 1 times the absolute value of 6x. We'll still have the absolute value of 6x. What's the absolute value of negative 1? It's just 1. So I don't need it anymore. That's why our absolute value of negative 6x plus 2 is the same as the absolute value of 6x plus 2. So 3. So the 3x, negative 3x squared. So that question was where we got the 9 from. Because here, the square is telling us I'm multiplying the negative 3x by itself. So our negative 3 times negative 3 is positive 9. We just applied the square to it to get there. Now, this here, because there's nothing else added or subtracted inside that parentheses, we can multiply it by itself and we're good. But if we had, say, negative 3x plus 2 squared plus 2, we're going to leave it. Because of the plus 2, it caused things to be a little different, a little weird. Yes. And if you remember when we graphed some of these with the horizontal stretch or shrink, I think it was last week, where the graph moved over as well. It wasn't just lined up like some of them. And part of that, and this is above and beyond, is dealing with the fact that we have a negative 3 there. To really look at the transformation and describe it, we have to factor a negative 3 out of both terms to really see the left-right movement. Because negative 3 out of negative 3 actually just x. We divided it. If I divide it from the negative or positive 2, I get negative 2/3. So our left-right movement is this 2/3, not our nice whole number. So it's part of the reason why I stay a little bit away from horizontal stretch or shrink, because it causes these kind of issues with it. But that is the last thing we're doing today. Hopefully, I think those assignment problems look familiar, yes? The exact same ones from yesterday. I'm not adding any of these transformations in. I just wanted to go over them and so that y'all see them, but the homework is still the same as it was yesterday.